Good afternoon, everybody. I hope that you're having a great day. Today, what we are going to do is we're going to look at a couple of things. We're going to look at, well, some more details or we're going to get into a couple more amino acids. If you remember, let me go ahead and share my screen and I'll kind of give a summary or high points of yesterday. Um, there we go. So today is day 4. This is day 2 of amino acids. Yesterday, where we were was we talked about our amino acids. We talked about them as being polar, nonpolar, and aromatic. We introduced the single letter and three-letter codes for our 20 proteinogenic amino acids. And we took that group of amino acids, our polar amino acids, and we classified them as charged, and touched on this a little bit, uncharged. Those polar charged amino acids fall into two different ranges, positive and negative. Um, One thing that I struggled with as a student whenever I was learning my amino acids and my amino acid structures is I remember these classifications and I kind of like just it's like I took all the classes and threw them in a blender and tried to cook something up based on that. Because if you asked me to classify an amino acid, you said, how is phenylalanine classified? I'd be like, ooh, phenylalanine. Let's see, where should I start? I'm gonna go with negative nonpolar. And that was something that if you gave me the follow-up question of, well, is that a charged or uncharged amino acid? I'd be like, ooh, great question. I just a moment ago said that it was negative nonpolar. I'm going to go with it is uncharged. Yeah, there we go. But let's take that sentence and take that idea and deconstruct it a little bit. Well, if something has a negative charge, does it have a pole, Pole, to it? It absolutely does. A negative pole. It is a dipole. It has a dipole. By that, by something having a negative charge, could it in any world be nonpolar? No, those two ideas are completely contradictory. I bring that up not to confuse you, but instead to say, like, well, let's think about this. Anytime you're confronted with how do you classify this? Well, think about, okay, it's got a positive charge. Oh, positive, indicating that it has a cationic pole, Pole. Um, so we talked about these different groups, and then we talked about basically how to approach amino acids given um, their pKa's. How many different ways can we draw an amino acid? How many possible ways can be drawn? And just as a pretty important point from yesterday, if you have a molecule with three pKa's, and I'm speaking generally, a molecule, if you wanted to go specifically and say if you have an amino acid with three pKa's, is that a monoprotic, diprotic, triprotic, tetraprotic, pentaprotic? If it has three pKa's, how would you define that molecule using that terminology? Well, three pKa's indicate that it has, well, three ionizable groups, three protons that can be lost. So if an amino acid has three pKa's, that's a good sign for you to know that, aha, it's a triprotic amino acid. If it has two, well, then it's a diprotic amino acid. Spoiler alert, our amino acids are not going to be monoprotic or tetraprotic. Everything's either a diprotic amino acid or a tetraprotic amino acid. Okay, so this was the area that we really focused on yesterday. are polar charged amino acids, and we looked at our positively charged and negatively charged amino acid. Could anyone give me in the chat the two one-letter codes for your negatively charged amino acids? D and E. Perfect. That's aspartic acid and glutamic acid. D is aspartic acid, E is glutamic acid. Now, if you think about those functional groups, I got to be honest with you, aspartic acid is my favorite amino acid. Um, and if you're thinking, will I have a favorite amino acid by the time this class is done? You will. You will. It's fun. It's what makes science and biology fun and biochemistry. Um, I'm optimistic that you will. Um, and the reason that I like aspartic acid is because for me, it's a really good jump off place to draw an amino acid. It's almost like if I take a hiatus, if I don't do something for a long time, if I don't draw an amino acid for a long time, and then someone's like, draw an amino acid, I'm going to go to aspartic acid because it's almost like riding a bike. It's my comfort zone. And the R group for aspartic acid looks like this. Whenever I do that, I immediately, there's a couple of things that come to mind. First of all, give me a letter if you think that this is protonated, and a number if you think that this group is deprotonated. A letter for protonated and a number for deprotonated. Perfect. That is the protonated form of that R group. Now, very generally, give me a letter if you think that this is going to be in a basic environment or a number for an acidic environment. I'm not asking for a specific number, and yeah, it's all relative, but it's more than likely that you're going to see that where it is protonated in an acidic environment. Okay. Now, this group specifically has a pK of about 3.25. So that group is going to be protonated at a pH of below 3.25. And that's really acidic. And I understand like acidity and basicity, it's all relative. Five is more acidic, or a pH of five is more acidic than a pH of seven. Sure. But I'm going, just in a very general sense. Okay. So if there's something where, or if there's like a important takeaway from yesterday, it would be, I want you to be able to, okay. So that's a great question. Okay, so let me go ahead and let me think how to construct my response. Okay, here we go. So this group right here, I've drawn it where there is, okay, actually, let me take a pause. I'm going to switch colors. I'm going to switch to the highlighter. That is my functional group. That functional group is a carboxyl group. And I know that a carboxyl group basically has two different ways of being, produced, or it exists in two different ways. One way is COOH, and the other is COO minus. Now, this one on the left-hand side, between the two of them, that one has the proton. Now, whenever I think of an acidic environment, I've got a lot of these right here, H3O plus, a ton of hydronium ions. And just like you did in Gen Chem 2, we're not going to draw hydronium ions or write that all out because I don't know about you guys, but whenever I was writing the 3 and the O, I got a little bit tired. So it's much faster and less exhausting for me to just say, done. Whew. Saved a lot of time and energy there. So in an acidic environment, I have tons of these, so many protons that those protons are not only in my solution, but they're basically going to every single molecule that's in that solution and saying, hey, I'm a proton, I'm here. I'm just going to hang out with you. Whenever this is protonated, which is how I've got it drawn right here, I know that I've got lots of protons floating around as opposed to a small number of protons or comparatively a high concentration of hydroxide ions. Does that help? Okay. Okay, cool. And so that's just kind of my indicator. And I'm happy that you asked that because one of the things that I know that I struggled with and I've had students struggle with in the past is something that we talked about, I think, on our second day, where I want you to not immediately think, oh, protonated means positively charged. Because a carboxylic acid, that's protonated, no charge whatsoever. The deprotonated form of a carboxyl group is negatively charged. So I'm happy that you asked that because that is sort of a trap to fall into and see this and be like, oh, well, yeah, there's a hydrogen there. I see that. I'm good, but shouldn't it be positively charged? No. And it all has to do with individual functional groups. Okay. So now we're going to move ahead to look at our other amino acids. Yesterday we looked at about five of them. Today we're going to look at the remaining 15 because we've got a grand total of 20 proteinogenic amino acids. We can still use this polar and non-polar categorization. Then we can also go ahead and draw a big circle around our um, our aromatic amino acids. One of those aromatics is polar, one of them is non-polar. Now, when it comes to kind of organization of amino acids, you might find some textbooks or resources online that identify polar, non-polar, aromatics and keep them all separate. But the great thing about chemistry and biology for that matter is you can classify something and it is true. This is nonpolar, but it can also be something else. I always like to use the word duplicitous or duality. The duality of tryptophan is that it is aromatic, but it's also nonpolar. The same, those two things can be true simultaneously about that amino acid. Now, to take a deeper dive into one of these groups, let's look at our nonpolar amino acids. Now, when it comes to our nonpolar amino acids, I've got this list of pKa values. These pKa values, well, first of all, give me a number in the chat. How many pKa values do you see per amino acid, per single letter code? 2. Okay, you're absolutely right. Now, what I want to do is I want to go through each one of these and assign these single letter codes. We'll start in the upper left-hand corner. This is the amino acid proline. Proline is kind of interesting because where I'm going to draw a red dot, that is my alpha carbon. And I can zoom in just a little bit. I hope that you guys, Maddie, 100%. That does mean these are diprotic. So I'm happy that you asked that because basically what that means, and you can take this to the bank, your nonpolar amino acids are all diprotic, which is a great success because, and I'm usually pretty disrespectful towards the nonpolar amino acids, but it's only because they're boring. And what I mean by that is every single one of these has a titration curve that looks like this. Done. Every single one has a diprotic or a titration curve with 2 pKa's, and that's about it. Now, I think that's helpful because, well, that means that the R groups for your nonpolar amino acids, they kind of don't really do anything. With that in mind, I want to show you proline, then highlight a couple of other ones, and then we're going to kind of come up with some kind of broad stroke explanations or commentaries on these. So all our non-polars, they're diprotic. I'll write that up top here. They're all diprotic. With this one in the upper left-hand corner, proline, I can zoom in, and I hope that this zooms in for you guys. I'm going to check if it does. Okay, good. What I want you to notice about proline is that we've got a bond going to a carbon. And that carbon there, it should have two hydrogens on it. That's not like some magic carbon that only has two bonds to it. But what I want you to notice about proline is that the R group is actually attached to the N termini of this amino acid. So it kind of makes a ring. Now, this is a ring structure, but it is not an aromatic structure. This is a five-membered ring, and proline is kind of an amino acid that presents some problems. It presents some problems because it has some limit or it has limited flexibility. This R group can't move around like all of our other amino acids do. So, what I want you to notice about proline is that the R group connects to the N termini. That's an important takeaway. Proline has the single letter code of P, the three-letter code of, oh, I knew I was going to zoom too far. Yep, I knew it. There we go. The three-letter code of PRO. Our next amino acid is glycine, and I'm going to kind of burn through these pretty quickly because there's not a lot that's interesting about them. Glycine, single letter code of G, three-letter code of GLY. Leucine, L, three-letter code LEU. If you look at glycine, the R group is nothing but a single hydrogen. Glycine is the smallest amino acid because the R group is just a hydrogen. Leucine, leucine has, well, a branch structure with three carbons coming off of it. Tryptophan, tryptophan's a kind of interesting structure, and I think tryptophan's the amino acid that lots of people have some familiarity with because they think, oh, Thanksgiving, turkey, tryptophan. That's the one that makes you sleepy. And I think that there is some physiological relevance to tryptophan in terms of it might make you sleepy. But tryptophan is an amino acid that's commonly seen in synthetic pathways for making like hormones. Um, Tryptophan has a three-letter code of TRP and a single letter code of W. W might seem like kind of odd, but that single letter code is coming from the phonetic pronunciation. So if you said tryptophan, like tryptophan, it's almost, yeah, so there's that. You've got that. In addition to that, I've always kind of looked at this two ring structure. One of my students told me this whenever I was a graduate student. They said, oh, it makes a W because it's two rings. You guys are going to have to be able to identify amino acids on exams and quizzes. You won't have to draw them, but I think that it's helpful to go ahead and kind of commit that to memory. So tryptophan is W. Valine is V. VAL is the three-letter code. It has three carbons as its R group. Alanine is ALA. And it has a single methyl group. Isoleucine, single letter code is I, and the three-letter code is ILE. Which, if you think about that, well, why isn't it ISO? Well, think back to organic chemistry. Everything is ISO. You have isomers. That would be very complicating and confusing on those. Phenylalanine is F, and oh, sorry, I got ahead of myself. The single letter code is F, and the three-letter code is PHE. Methionine is M and MET. So almost all of your nonpolar amino acids, their first letter is the single letter code. In addition to that, almost all of your nonpolar amino acids, the first three letters are the three-letter code. There are a couple of exceptions, those exceptions being tryptophan and isoleucine, and that is it. Methionine is an interesting amino acid because it has what only one other amino acid has, and that is a sulfur in its side chain. Now, with that in mind, if you look over to the right, I've got a list of all your diprotic amino acids. All of these do not apply to this list. Alanine, phenylalanine, glycine, isoleucine, leucine, methionine, N is not one of these. Proline, Q is not one of these. S is not used on this. T is not used on this. V and W. So, one thing that I want you to take away from this list here is that you've got if the check marks indicate all of your non-polar amino acids, well then these scribble outs, those are amino acids that are diprotic and they are polar. So just as a little bit of a question here, how do you think, I mean, these four amino acids where I've scribbled them out, these are polar. They are polar amino acids, but these four amino acids do not have an ionizable R group because they don't have a third pKa. So I'm going to jump back and I want somebody to propose how you would classify those four amino acids given these options. Aromatic, nonpolar, polar uncharged, polar negative, polar positive. Spoiler alert is they are polar, but they don't have a third pKa. We talked about our boom, boom, live it up, live it up. Miracle, that's absolutely right. These are our polar uncharged amino acids. Now, I scribbled these out just to kind of eliminate them from what we're looking at on this slide, and we're going to come back to those so I can introduce those to you. But thank you very much for that response. So these are all of our nonpolar amino acids. When you look at these nonpolar amino acids, one of the things that I want you to recognize is that the R groups, I'll write it up top. They're diprotic. R groups make, or sorry, R groups are mostly hydrocarbons. So these R groups are mostly hydrocarbons. Um, I'm going to ask you a question, and I want you to give a letter for love and a number for dislike. How do how do hydrocarbons feel about water? Yeah, they dislike. They do not care for water. What is what's the observation? What's the effect that takes place when you've got a hydrocarbon in an aqueous solution or a water-based solution? What's that known as? Hydrophobic effect. So the hydrophobic effect. Okay. Now, what we're building towards is we're looking at individual amino acids. We're looking at these R groups. We're not looking at these R groups for the purposes of, I want you to memorize these so that you can get really, excuse my language, but badass tattoos And so you can draw them and graffiti them everywhere. Instead, I want you to look at these structures and think about how these different R groups would interact in an aqueous environment. So the hydrophobic effect is kind of the driving force or the driving principle behind hydrocarbons interacting with other hydrocarbons. Do you think that isoleucine here, ILE, the R group for isoleucine, if that was in an aqueous environment, do you think that it would maybe interact with the R group for phenylalanine? Well, they're both hydrocarbons. One's a ring and one's more linear, but in an aqueous environment, they're going to be like, okay, cool. We can interact with one another. Now, these molecules that we're looking at are the building blocks for proteins. So if we have a protein that's in an aqueous environment that has a bunch of non-polar amino acids, they're going to interact with one another. And when they interact with one another, that is going to result in the shape of the protein being determined. So this is the hydrophobic effect. These non-polar residues will interact, and that's going to cause the remainder of the protein to take on a specific shape. Now, that got a little bit abstract, but from what we've talked about or at this point in the class, can you give me a number if you say, okay, I'm good, or a letter if you've got a question about something and you're confused about something? Okay. And if you're inclined to type a letter, go ahead and try to put your question together in a chat or just, jot down your notes and you can hang out for a moment after class is done. And I'd be glad to talk with you and try to clear things up. Maybe we'll clear things up along the way. Okay. So our non-polar amino acids, these are those non-polar amino acids. They all have two pKa's, meaning they are diprotic. They all have titration curves that look like this. And then the last thing that I want to talk about is let's look at phenylalanine here. And we'll do that a similar question from what we saw yesterday. Um, let's go with nobody knows. 13. Okay. I've got four answer options. Phenylalanine, as it's displayed right here, that model of how it's displayed right there would most commonly be found at which of the following pHs? 2.57, 2.59, 13, or nobody knows. In order to answer this question, what will be helpful is to look at phenylalanine. F has two pKa's, 9.24, 2.58. Okay, so I'm getting a peppering of A and B. I'm not getting anyone answering D. You're right. D is not a good answer. C is also not a good answer. A and B are arguably the best answers. Our pH, let's say that our pKa that we're interested in is 2.58. If we were to put this molecule into a solution with a pH of exactly 2.58, half of that molecule would look like this, and then there would be other copies of this molecule where the C termini is deprotonated. And so our backbone would look like this, NH3 plus, C, R group, C, O, O minus, and then H here. So half of it's going to look like this, and then the other half's going to look like this. That's if the pH was exactly 2.58. If the pH is 2.57, that's more acidic. So there are more hydrogen ions. And so the majority of our molecule is going to look like this right here. There's going to be more of it that looks like that than this right here. The reason being is it might be 51% looks like this and 49% looks like this. But 51 is still more than 49. And the reason for that is because, well, more hydrogen ions resulting from a more acidic, or sorry, a more acidic environment means a lower pH. So 2.57 is our correct answer. So A is the correct answer there. Okay. 2.59, well then you've got 51% that looks like this. And 49% that looks like this right here. Okay. Now, our next groups of amino acids are aromatics. Like I said, tryptophan is an aromatic. Tyrosine is also an aromatic. Now, what makes them different from one another is that if we look at all of the pKa values, actually, let me go ahead. We know tryptophan is W, phenylalanine is F. Now we're going to look at our polar residues. Our polar residues, well, tyrosine is Y. TYR is our three-letter code for tyrosine. Can you tell me how many pKa's does tyrosine have? 3. So tyrosine is a triprotic amino acid. It's a polar residue. It's a triprotic amino acid. That means that this hydroxyl group can have a negative charge. Can anyone tell me then why is this not classified as a polar negative amino acid? And that's a kind of lengthy answer, but I'll give you a minute to think on that one. Why is this not a polar negative residue? Resonance, I don't know. Okay. Well, the correct answer for that is we've got to think about the definition for why something is classified as a polar positive or a polar negative residue. It has to do with what is the charge at a neutral pH. So yesterday we talked about aspartic acid. Uh, okay, so Miracle, you're on the right track. This group at a neutral pH, this will be NH3 plus because that group has a pKa of 9.11. Our C termini for tyrosine is 2.20. Our R group for tyrosine has a pKa of 10.07. So tell me what the charge of the R group will be. Okay, so it will be the reason that it's not polar negative is because this group, the R group, which is all that we care about, that R group at a neutral pH is going to have a charge of 0. Chen, you're absolutely right. Okay, so cysteine. Cysteine is a triprotic acid. This proton can be lost. That's a sulfhydryl group. So we've got an alcohol and a sulfhydryl group. Cysteine has the three-letter code CYS. and a single letter code of C. I'm going to write these pKa's out. 10.25. The C termini for cysteine is 2.05. The R group is 8.00. Tell me what the charge of the R group for cysteine, just the R group. What's the charge of the R group for cysteine at a pH of 7? Perfect. It's 0. Cysteine can have a negative charge, but not at a neutral pH. So when I jump back and we talk about polar charged, polar uncharged, or polar positive, that has to do with, and I'm going to add this and then I see your question, Maddie. Positive, negative, R group has this charge at pH of 7. Okay. Now, Maddie, if you know what I'm going to do, I'm going to add a slide to the PowerPoint so that I can kind of interrupt what I'm doing and go ahead and do a little drawing. Okay, so that's where, okay, aromatics, but then I wanted to come to the polar uncharged. I've added the slide. Okay, here we go. So let's look at cysteine. And we're going to work through this because this is the important part of a very, very important skill to develop. Cysteine at pH 1. Everything's going to have a proton on it. Everything that can have a proton will have a proton. So the first thing that we do is we draw the backbone. H3N plus. Alpha carbon, carboxy end. We draw every peptide backbone or every amino acid backbone in the N to C direction. My alpha carbon has a hydrogen. Then my R group, let's look back. I've got CH2, SH. Okay, so CH2, SH, a sulfhydryl functional group. Now I'm going to write out my pKa's. My pKa's, this is 8 for my R group, 8.00, 2.05, and 10.25. Is this what the molecule will look like at a pH of 1.95, or the predominant form of the molecule will look like at a pH of 1.95? Give me a number for yes and a letter for no. Yeah, that's absolutely what it's going to look like at a pH of 1.95. What about 1.96? Yep. If I continued on and I said 2.04, yes, this is what the predominant form of the molecule is going to look like at a pH of 2.04. Now, I am imagining that I'm titrating this. I'm going to draw my titration curve. pH is my y-axis. X-axis is OH equivalence. I'm going to put 3 dots on this to indicate my 3 pKa values. And I'm going to try to space them out pretty evenly. The first group that I'm going to deprotonate happens to be my C termini. And that molecule will look like this. H3N plus C O O minus and H. CH2 SH. Sulfhydryl group remains intact. That's what my molecule looks like. Well, actually, if my pH equals 2.05, that's a 2.05, What can you tell me about the abundance of those two molecules? They're equal. It's 50-50. If my solution pH is exactly 2.05, half of the molecule looks like this, and half of it looks like this. Or, sorry, half of the copies of the molecule in that solution. Now, when I go to a higher pH, well, then I'm going to favor this one right here as my pH increases. So I'm going to be reducing the form that's on the left and increasing the form that's on the right. I'm going to write my first pKa of 2.05. Charges that I'm keeping track of, well, on the left-hand side, my molecule is an overall charge of +1. In the middle, or sorry, on the right-hand side, well, we've got a positive charge and a negative charge. Those effectively cancel out. So I'm looking at a 0. Next up, well, what's my next pKa? Happens to be my R group with a pKa of 8.0. And these numbers, your pKa's are always going to be provided to you whenever you need them. If you don't need them, I won't provide them to you. 8.00. Okay, so now I've got backbone H3NCCO O minus H. I'm going to go ahead and put my plus sign on there so I don't skip over that by accident. CH2, and now I've lost that proton from my R group, so S minus. My sulfhydryl group has been deprotonated. If my pH was 8.0, I've got basically 50% this, 50% this. Effectively 0 of this one right here. Because all of my copies of my molecule undergo transformations. They get deprotonated. They continue getting deprotonated. I deprotonate one group at a time. The overall charge for this molecule that's on the far right is -1. Then my last form, my fourth form of this molecule, pK of 10.25. So I've adjusted the pH of my solution to be or above 10.25, and that's when I'm going to have my molecule that looks like this. H2N, C, C, H, CH2, S minus. What's my overall charge for this molecule? -2. So I have 4 different forms that cysteine can take on. Cysteine can have a positive charge as high as +1 and as low as -2. Is cysteine ever going to have a charge of -3? Nope. What about +2? Nope. This is the range. These are the options. These are the ways in which cysteine can exist. Now, to come back to our R group and our definition, this is a polar residue, but it is not a polar negative residue. And that sounds so confusing because you're looking at this R group and you're thinking, that's negative. It can have a charge of -2, but this is not going to be the abundant form or most abundant form at a pH of 7. So it's kind of a semantic or a definition as to why it's not a polar negative amino acid. Does that make sense? Okay. Now, to complete this and to look at my titration curve, I'm going to go ahead and draw in some lines. Switch to green, and so, and that's drawn above it, but that's kind of an accident. I'm just not good at drawing sometimes. Usually I'm really good at drawing. That's my titration curve. So it's about the current pH. Great question. It's about a neutral pH. That definition, that classification of polar negative, polar positive specifically relates to the neutral pH. Great question. Does that actually answer it? Okay, good. That's a tough thing to wrap your mind around because it's like, but it has to do, those definitions have to do with the specific pH. or the specific neutral pH. Okay. Now, one of the things that I always like to do is whenever I draw a titration curve, I'm going to label my x-axes. My x-axes, where my coordinates are. I'm going to label my y-axis, and I'm going to say 2.05. My y-axis labels are pH measurements, but I'm only going to be writing the pKa's because I don't really care that much about other pHs. 10.25. Now, what's important to know about this and to note about this is whenever I reach or whenever I say my pH is equal to my pKa, I've got 50% that looks like this and 50% that looks like this. 50% is a percentage. It's the same as a ratio of 0.5. So my pH equivalents here are 0.5. So half of it looks like this, where I've got an X, and then the other half looks like this. What I like to do at this point is I like to draw a dashed line. If I am to the left of this dashed line, the predominant form of my molecule will look like that. So if I am on the titration curve, if I were to give you this and say, okay, what does the predominant form of your molecule look like at that blue dot right there? Well, it looks like, and I'm going to label all my forms, A, B, C, and D. My molecule looks like A at that specific pK, or if I'm at that specific position on the titration curve. Now, what if, to add a little more complexity to it, what if I'm right here? Okay. Now, before anyone answers this, what I want to do is kind of walk through the development. We've got another coordinate point that relates to 0.5. And then I'm going to go ahead and give my last pKa value another 0.5. I'm going to draw a dashed line up from that 0.5 through my pKa. I'm going to do the same thing way over here. Okay. Now, I've given you this dot. What I want to do is ask the question before we get to about that dot. I think everyone would kind of agree that if I was in this position where I drew the arrow, my predominant form of my molecule looks like B. A is still in there, but B is the predominant form. At that point on my titration curve, it might be 56% looks like form B, and that means 44% looks like A. Okay. Now, with that in mind, we have this point on our titration curve where, yeah, if we move to the right, if we're moving to the right, what becomes more populous or what becomes more common? Form A or form B? If I'm moving to the right. B. You're absolutely right. B becomes much more abundant. And as B becomes abundant, A decreases. So we've got this balance shifting towards B. Now, if I continue on and I continue on moving to the right, where this dot is, what form of my molecule is most abundant? This dot right here. B. No doubt about it. Okay. Now, where it gets a little bit tricky is we went kind of through a journey here. When we were here, I said that it was like 56-44. When we were right here, it was like 60-40. Right here, oh, it's like 70-30. Does everyone give me a number if you say, okay, I follow that? And a letter if, oh, wait, stop. Okay. So we're continuing moving to the right, and we're seeing the percentage of form B increasing. At some point, would you agree that we are going to reach 100% of our molecule effectively is form B and 0% is form A. And well, 100% is all of it. So what does that mean for form C and D? That's also 0%. That's also 0%. Can I get a number if you follow that logic? And a letter if, wait, stop. Okay, great. So we're continuing to increase until we get to 100. That 100 point, where all of our molecule, where all of our molecule looks like form B, is right here, smack dab in the middle of our asymptote of our titration curve, where our line becomes vertical. Now, as we continue to move right, what is going to happen? But some of B is going to be converted to form C. So could somebody give me numbers, or actually tell me, first of all, what is the identity of the molecules in my solution where I have that dot? What forms? A and B, B and C, A and D, B and C. You're absolutely right. Now give me some rough numbers. You don't have to be absolutely right here, but give me an estimation. Amount of B and amount of C. We'll list them in that sequence. 60-40, 60% B, 40% C. I like it. Now, if we continue on, we're going to eventually reach this point, our pKa, where we've got 50-50 again. So we are slowly but surely converting this form into this form. And then once we've converted all of B into C, then we're going to convert all of C into D eventually. So what I always like to do whenever I draw a titration curve is I like to pick out these points on my titration curve. I know my pKa's. That's where I've got a 50-50 ratio. Then I've got these X's. This X is where 100% looks like B. This next X is where 100% looks like C. If I wanted to, I could come up with another X over here. Well, that's effectively where 100% is D. Now, this is important, and this is valuable information because you understand the progression of our molecule, how it changes over time, how it changes as our pH of our solution changes. Can everyone give me a number if you follow? Okay. Okay, cool. Now, this is cysteine. Cysteine is a polar uncharged amino acid. If we look back at tyrosine, that is also a polar uncharged amino acid. Serine, asparagine, threonine, and glutamine are also polar uncharged amino acids, but what's important to know about these amino acids is that they are all diprotic. Serine has a single letter code of S, three-letter code of SER. Asparagine has a single letter code of N, and glutamine has a single letter code of Q. The three-letter code of asparagine is ASN. The three-letter code of glutamine is GLN. Threonine has a single letter code of T and a three-letter code of THR. Now, one thing that folks have a tendency to kind of get tripped up on is they look at asparagine and glutamine and they say, oh, well, that's got a nitrogen. That nitrogen certainly at a very acidic pH can take on another hydrogen, so it can be positively charged. That is not the case. That NH2 there is basically counteracted by this carbonyl carbon. So we've got something that has effectively two partial negative charges. So they kind of compete, and neither one of them wins a proton. So those are not, asparagine and glutamine are not ionizable groups. Now, one thing that I always like to bring up is, does anyone remember, and add it to the chat if you remember what my favorite amino acid was? D for aspartic acid. ASP is my three-letter code for that. I'm going to jump back and let's take a look at the three-letter or the R group for aspartic acid. It's right there. CH2 followed by a carboxylic acid. Okay. Now let's jump ahead and look at the R group for asparagine. This is where my R group begins. We've got CH2 followed by a carbonyl carbon, and it's almost like we're about to draw on a carboxylic acid, but then we get NH2. So it's an aminated carboxylic acid. So I always like to bring that up as a contrast because that gives me a way of remembering, okay, I know aspartic acid, asparagine. Oh, dang. Those two amino acid names are very similar to one another. Their structures are very similar to one another. Glutamine, well, glutamic acid has the same basic structure as glutamine. The difference is that rather than having a complete carboxylic acid, glutamine has that NH2 there. Okay, so we've looked at all of our 20 proteinogenic amino acids. We've looked at the pKa values for them. Most of your amino acids, most of your proteinogenic amino acids are diprotic, and most of your diprotic amino acids are your non-polar amino acids. There are four that are polar uncharged amino acids. There are two polar uncharged that could adopt a negative charge, but it has to do with the specific neutral pH at which they have that negative or that negative charge. Now, I'm bringing all of this up because these are questions that you will absolutely see on your quiz. Classification of amino acids. I will give you a single letter code and I will say, what's the best way to classify this amino acid? What I would recommend doing is I like to start small and I like to say, okay, aspartic acid, glutamic acid. That's two amino acids that make up my polar negative amino acids. Then I say, all right, well, that's only 10% of the ones that I need to know, but I'm going to go back here and I have my major groups. Two amino acids are polar negative. Three are polar positive. That means, and then I can go back and say 11 are polar, 9 are non-polar. So if two are polar negative, three are polar positive, that leaves nothing but 6 polar uncharged. My 9 non-polar residues, and then I always just kind of drill into my head, there are 3 aromatic residues. I've always thought that when you start small and you kind of take this 20 proteinogenic amino acids and break it down into smaller pieces, it's easier to process that information. Okay, now we're doing all of this because, and looking at this titration curve and coming up with a point where 100% of my molecule looks like this, because that is a physiologically important part of every amino acid. Okay, now I'm going to take a drink of my drink. And I'm going to tell you that I've written your quiz for Monday. I will be sending out study ideas for that. And in addition to that, for your quizzes and your exam, you can use a single 3-inch by 5-inch index card. You can use the front and back, and you can write on that. So anything that you need to have as like a reference point or as a reference, put that on there. The test is not open book, it's open note card. The quizzes are not open book, they are open note card. My expectation is that, and I can scrub through the video if you take this on Proctorio, or if you're in person, you bring that with you. Um, that's I am fine with that. I have no problem with that, but you're limited to that 3x5 index card. Um, and what you put on the index card for the first exam, you might change it for the second, you might change it for the third, you might change it for the final. Um, it does not have to be handwritten. If you want to print something up, that's fine, so long as it ends up being 3x5, 3 inches by 5 inches. Um, and some people will get like a piece of paper and just measure out. Oh, is this 3 inches? Yes, cut. By 5 inches, cut. And cut it into that. You don't have to go to the grocery store and buy like index cards or anything special like that. So you can use that for this quiz upcoming on Monday. Um, does that mean that I'm going to make things infinitely difficult? No, I'm not. Does that mean there's still rigor with the material? Absolutely. Um, you know, just like I mean, I will give you the PKA, so I don't need you to memorize, or that's not worth your time to memorize those, but you need to know what to do with them. You need to know what are the implications of a solution with a pH less than a pKa. What does that mean for that functional group? Okay, so where are we? I'm not really saying where are we. I was just saying that to stall for a moment. Okay. Our talk of amino acids is a good way to lead into a discussion of protein structure. Now, there are, spoiler alert, 4 levels of protein structure. The primary structure is the amino acid sequence that the polymer of amino acids has been assembled. And that's generally referred to as, and we've used this terminology, N termini to C termini. The stabilizing force that, well, stabilizes those are peptide bonds. Peptide bonds are an example of a covalent bond. Your primary structure is read from an N termini to C termini direction. So N termini to C termini, stabilized by peptide bonds. Typically, your 1 letter and 3 letter codes are used for labeling a sequence, labeling a protein sequence, and that might appear as ARK. That's what's known as a tripeptide that follows the sequence of alanine, arginine, lysine. Or you'd see it as ALA, ARG, LYS. The primary structure is the amino acid sequence. A peptide or anything less than 50 amino acids, or sorry, a peptide is anything less than 50 amino acids. Anything more than that is considered a protein. Is that a hard and fast rule? No. That's just kind of a convention. If you're talking about something that's a polymer that's 125 amino acids long, chances are it's going to be referenced as a protein. But that's not absolute. Now, when it comes to amino acids and interactions, we need to know about intramolecular as well as intermolecular. Intra is bonding within a molecule. And remember, when it comes to bonding, we're talking about our valence electrons, so the outermost electrons that are being shared. Bonds are going to be classified as polar covalent, non-polar covalent, or ionic. Predominantly, we're going to be talking about um, polar covalent bonds. Specifically, we'll talk about interactions between an ion charge and a dipole charge. We'll also talk about anions and cations. I know that it's always tempting to see something like this and say, okay, Na plus and Cl minus. I should be on the lookout for sodium. Not really. If we look at a amino acid like, let's go with cysteine. This this negatively charged sulfur is a really good anion. So a cation in solution like sodium it's absolutely going to be attracted to that. A chloride anion, by contrast, is not going to be attracted to that. So we do have inorganic cations interacting with um, organic anions and vice versa. So those are R groups that will interact with things in a solution as well as interact with one another. Now, a peptide bond. Well, a peptide bond is going to be a structure that's resonance stabilized. Now, what I'd like you to think about with respect to a peptide bond is the backbone of individual amino acids. NCC. NH3, positive charge. H, I'm going to draw an R for my R group. And then OH. And I'm going to put it as negative because at a physiological pH, that's basically what my C termini is going to look like. This will react in a condensation reaction with another NH3 plus O minus. So the groups that will react with one another in a biological system are the C termini of one amino acid and the N termini of another amino acid. The result will be this: NH3 plus, and actually, you know what I'm going to do is I'm going to switch colors whenever I get to my other backbone. My alpha carbon. I lied, but now I caught myself before I totally lied. N, H, H, pairs of electrons, R group, R group. So these groups that I circled on the left form that structure, and this bond right here, known as a peptide bond. That peptide bond is a covalent bond, but one of the things about it that's tricky to appreciate is that it is resonance stabilized. So what that means is that it's fairly strong. It has approximately 60% double bond characteristic. So this structure that I've got a big circle around will sometimes look like this, or one of the resonance structures looks like this that I've also circled, where you have that double bond between the carbon and nitrogen. How did you get that? Well, by making a negatively charged oxygen. So that's a resonance stabilized structure. It's rigid, it's inflexible, and what that means, or that bond is also strong. One thing important to know about this is that the peptide bond for all intents and purposes will never have a negative, all right, let me rephrase that, have a charge. So what that means is many times when you're looking at a peptide, you don't care about the N-terminal pKa or the C-terminal pKa of individual amino acids because a peptide bond isn't going to have a charge. Now, what I'm going to do is, well, we talked about, okay. So I want to show you guys a couple of things here. We talked about a Zwitterion. The Zwitterion form of any amino acid is positive and negative charges, I'll say simultaneously exist on an amino acid. So part of the molecule is positively charged, part of it's negatively charged. Okay. If we go just as a little bit of a refresher, if we were to look at cysteine, this is a Zwitter ion form. Arguably, this is also a Zwitter ion form because the N termini and C termini both exist. They coexist. Now, that's an important thing to keep in mind. That's an important thing to know. Calculating a charge. Well, charges of amino acids, well, they'll be +1, +2, +3, -1, -2. Or sorry, charges mostly are going to be +2 all the way to -1 or +1 all the way to -2. And that's just a matter of looking at the molecule that you've drawn in the different forms and saying, okay, well, here's a charge, here's a charge, here's a charge. Let's add those up. +1, -1, -1. Okay, our overall charge is -1. Can I get a number in the chat if you follow that? And a letter if you don't follow that. Okay. Now, PI calculation. This is a unique pH at which 100% of a molecule has a charge of 0. Okay. Now, a fair question there is, why do I care about when it has a charge of 0? Could I get a number in the chat if you've ever heard of whey protein and a letter in the chat if you've never heard of whey protein or whey proteins? Number if you've heard of it. Okay. For those of you who have heard of whey proteins, maybe you've made or you've used a whey protein. And one of the things that, from my experience with whey proteins, is that I'll add it to water and it doesn't go into solution. And so then I've got I'm gonna go with a glass here. I got water, and then I added the whey protein, and maybe it's a little bit like that. So, okay, cool. Some of it went into solution, but then I got these big clumps down here. And then I'll get a spoon or a fork and I'll just be like shh, trying to mix it up as much as possible. But there's some clumps that just stay. They don't go into solution. And so then what ends up happening is I'm like, I'm not gonna wait 20 minutes for this to happen. I'm just gonna drink this because it doesn't taste good to start. I just got to get it over with. And so then I'll do this number. I'll drink it. Well, these clumps of this protein that did not go into solution, these are insoluble. Sol. How about insoluble clumps? Okay. I bring this up because when a protein or an amino acid or a peptide, when 100% of it, or sorry, when it has a charge of overall or an overall charge of 0, that is the point where the molecule is least soluble. Okay. Now, thinking about that from the perspective of whey protein, that's almost like, well, that sucks. I don't like that. That's no good. But think about this from a biochemist perspective. One of the things that biochemists like to do is they like to take a complex mixture, like a cell with thousands of different proteins. And what they want to do is they want to extract one protein. And they want to separate that one protein from these 29 other thousand proteins. Well, if all of those proteins are soluble, but they can get one protein to be insoluble, well, then that's actually kind of good because you've separated your insoluble protein from the remaining soluble proteins. Does that make sense? So this property where this molecule is the least soluble is kind of it's a great thing, really. So when it comes to PI, when it comes to any biological molecule, it's important to know the PI because then you can say, oh, all right, well, I want to precipitate or separate or make my protein insoluble. I've just got to adjust my pH to hit that specific PI, and then my protein just falls out of solution. Now, how do you calculate a PI? We've already kind of visualized the PI. I'm going to take you back for a moment to right here. I'm going to erase some of my percentages here. Okay. Um, I'm going to go with here's my letters A, B, C, and D. Um, what letter corresponds to my molecule with an overall charge of 0? Cysteine with an overall charge of 0. B. Okay, great. Now we have picked out 2 points on our titration curve where we have a or where we have 100% of a molecule. Which one of those is the point at which 100% of our molecule is B? Is it X or is it Y? X. X is where 100% of our molecule looks like molecule B. Okay. Now, a PI is a specific pH. Um, would everyone agree that this location on our titration curve is our PI? Give me a number if you agree, and give me a letter if, wait a minute, I don't follow. Okay. So that X corresponds to, well, it corresponds to a couple of different things. One, it corresponds to the location on our X-axis, but it also corresponds to a point on our Y-axis. Would anyone care to make an estimation as to what the point on our Y-axis is? What the coordinate is? About 5. I like that. Um, so I think, would everyone agree that it is more than 2.05 and less than 8? Would you go as far as to say that it's halfway between 2.05 and 8? Now, would you boldly go with me and say that you could find and calculate that specific point by adding 2.05 and 8 and dividing by 2? Okay, let's try it. Miracle gave us oh, maybe not. Okay, I like the hesitation. Now, spoiler alert, that is how it's done. That's how you figure out a PI. This is the location directly between those 2 points. So PI is equal to pKa plus pKa divided by 2. So in this case, we've got 8 plus 2.05 divided by 2. We're talking about 10.05 divided by 2. So that would be 5.025. And you might be thinking, whoa, mental math. Good job. Good job, Joel. Yeah, thanks. Just as a little bit of an aside, I like I like doing division like that. Another aside, one of my kids checked out the Harry Potter book, one of the really big thick ones from his library at school, brought it home, and we were like, "Oh, are you gonna read it?" And he was like, "No." And I said, "Oh, why not?" He said, "Why'd you get this big book?" And he said, "Because I like to flex on everyone." And I said, "Oh, okay, sounds good." But here's what we got, and this is our last thing for the day. And then we'll pick up on Monday. And I know this is a lot of information. Thank you guys very much for hanging with me. Anytime you calculate a PI, you're using two pKa's. You are trying to find the place at which a molecule, 100% of a molecule, has a charge of 0. Now, when we've been drawing out our molecules, and we've been drawing all the different forms of molecules, we took our structure when it was completely protonated, and we figured out what the charge was. Then we figured out, okay, when we deprotonate one group, that's our charge. Then we deprotonate another, that's our charge. Deprotonate another, that's our charge. Whenever you are trying to calculate a PI, you care about two pKa's. You care about the two that relate the charge from +1 to 0 and from 0 to -1. Those are the two pKa's that you care about. You don't care about anything else. I say that because sometimes when people are doing these calculations, they say, oh, I got to take all my pKa's and divide. No, you care about two pKa's. Now, what I'm going to do is I'm going to jump ahead, and I'll probably jump back and forth because we are going to do a couple of PI calculations. So we're going to do, let's do 4 PI calculations. We'll start with valine. And we're going to work through all of these amino acids the same way. Valine is a nonpolar amino acid. This is a diprotic amino acid. I'm going to Alt-Tab. You guys won't see this, but I'm going to toggle back and forth between my pKa values so I don't have to run back and forth. Valine is a diprotic amino acid, and it has two pKa's. Those pKa's are 9.72 and 2.29. The great thing about calculating the PI for a diprotic amino acid, you only have two amino acids that you have to work with, or two pKa's that you have to work with. So it's as simple as PI equals 9.72 plus 2.29 divide by 2. Now, anytime I have some sort of math like this, there's always somebody who's got their calculator out and they're like, haha, I got it. I knew it. I knew it. So 9.72, our PI is 6.005. Thank you very much, Miracle. Now, every diprotic amino acid, if I were to, this is where I will toggle back to a different slide. This, you could take every single one of these and add those two pKa's, divide by 2, you're done. That's the PI for every single one of those amino acids. Now, what's important to recognize about this is that with your diprotic amino acids, it happens. It's not a complete coincidence, but it's due to the simplicity of these molecules, it is the N termini and C termini. It will not always be the N termini and C terminal pKa values. So now what I'm going to do is jump back and let's calculate. Okay, so before I proceed, can you give me a number if you're good with calculating a PI of a diprotic amino acid, a letter if, wait a minute, stop the press. Okay. Now what we're going to do is we're going to do arginine. Arginine, 3-letter code of ARG, is a polar positive amino acid. It's diprotic. As a polar positive amino acid, here's what I always like to do. I'm going to list out my pKa values for this polar positive amino acid. I got to change my other screen. There we go. Oh, there we go. Okay. The N-terminal pKa for arginine is 9.04. The C-terminal pKa is 2.01. The R group has a pKa of 12.48. I know that arginine, and here's what I like to do whenever I draw an amino acid, is I'm going to draw a little box, put my R to indicate my single letter code, and then I'm going to say when this is fully protonated, on my N termini, I have a positive charge, so on the left side of my box. My R group has a positive on the bottom of my box, and then on the right side, it is neutral. My N-terminal group and amino group, when protonated, is positive. My R group, as a polar positive, has a +1. And my right-hand side, my carboxyl end, is neutral because a carboxylic acid, when protonated, is a 0 charge. So now what I'm going to do, so this is at a pH of 1. Now what I'm going to do is I'm going to make a list or make kind of number line. +2. That's my extreme. That's as cationic as arginine will get. I know that when I deprotonate one group, my next possible charge is +1. My next possible group, when I deprotonate that, is 0. After that is -1. I have 3 arrows because I have 3 ionizable groups, and I know that because I got 3 pKa's. On the far left-hand side, that's where I'm at my lowest pH. So I'm going to say 2.01. I'm going to list my first pKa. That happens to be my C termini. Do I care that it's my C termini? Nope, I don't. I care that it's my lowest pKa. After that, I'm going to list my next lowest pKa, which happens to be 9.04. It is triprotic. This arginine is a triprotic amino acid. Oh, I'm so sorry. Maddie, thank you very much for bringing that to my attention. Oh, dang. It's humiliating. I'll recover. I apologize for that, everyone. Sorry. I'm going to move forward, and I apologize. Okay. My last pKa, 12.48. Okay, so I've got my 3 pKa's. I've got my 4 possible charges. Does anyone want to go ahead and take a minute and try to calculate this one? I'm going to. And somebody's probably going to beat me to the punch. Miracle does it again. I did 9.04. Miracle did this as well. Plus 12.48 divided by 2 is 10.76. I only cared about these 2 pKa's, the ones that are on the left and right side of my 0 charge. I said we were going to do 4 amino acids. We've done 2 so far. Now we're going to go with, we will do cysteine. Nope, we already kind of did cysteine. That was 5.025. We will do tyrosine and aspartic acid. Tyrosine, TYR. And this, I'm not going to make the mistake I made a moment ago. This is a triprotic amino acid. I'm switching to doing triprotics just because the diprotics, it's easy. It's boring. But it's still nice and comfortable to do them from time to time. Okay, so it's a triprotic amino acid. TYR, tyrosine has a hydroxyl group. The pKa values for this, N, C, and R, those pKa's for the N termini is 9.11. The C termini is 2.20. And the R group is 10.07. Now, tyrosine is a little bit tricky. This is a polar uncharged amino acid. I'm going to draw my little box here, put Y in it, at a pH of 1. On the left-hand side, my N termini of this amino acid, it's going to be positively charged. My R group, as a hydroxyl group, as an OH, it will have no charge. The carboxyl end on the right side of that box, I'm going to put a 0 as well because a carboxyl group, whenever it's protonated, is going to have 0 charge. So what that means is my extreme is it's +1. This molecule is not going to be +2. It's going to be +1. It's a polar uncharged amino acid. My lowest pKa is 2.20, and that's the first one that I'm going to write. 0 is my next pKa. Or sorry, my next charge. My next pKa is going to be 9.11 minus 1. If I'm calculating my pi, I'm effectively done. This is my question. 2.20 plus 9.11 divided by 2 gives us a pi of 5.655 or 5.66. I can go ahead and move on and say, well, 10.07. And my molecule can have a -2 charge. But these number lines are all that you need to do. It gives you a good profile of the possible charges of the molecule, and it gives you a way to calculate, well, what's my pi? Now, to go with our last amino acid, aspartic acid. Well, aspartic acid is a ASP, is my 3-letter code. This is a polar negatively charged residue. It too is a triprotic amino acid. D, on the left-hand side, I'm going to put a plus because my N-termini is positively charged. My carboxylic acid R group is going to be 0. And my right side, or my carboxylic acid for my carboxy end, is also going to be 0. +1, 0. I need to copy my pKa's in just a moment. -1 and -2. My N-terminal pKa, C, R. My N-terminal pKa for aspartic acid is 9.82. The C-termini is 2.10, and the R group is 3.86. Would anyone care to calculate my pi for aspartic acid and add it to the chat? Almost. One more step. You got me. That was because I messed up with that die try thing earlier. I appreciate that. Miracle is making sure that I'm still awake. Thank you. And I think that I am. 2.98. Absolutely right. 2.10 is our lowest pKa. 3.86. And then 9.82. We cared about this pKa and this pKa. And that's it. One thing to consider is the variety of questions I like to ask. I like to ask questions about, and I've kind of I've alluded to this a little bit, is I like to ask questions like, could this amino acid have this charge? In which case, if you start with this sort of approach, you'll be able to answer that question. So a phrasing of that would be something like, proline can have a charge of +2. Aspartic acid can have a charge of -2. Well, for aspartic acid, yeah, true. Aspartic acid could have a charge of +2. Nope, because aspartic acid can be +2, 0, -1, or -2. That's the spectrum, or that's the range that aspartic acid can take on. So when you give us these on quiz or exam, we will assume pH of 1, and then we'll figure out the charge on the R group to then find the pi values. That is how I like to approach it. Drawing the molecule at a pH of 1, to me, is the easiest thing. because then you're saying everywhere that a proton can be, this is what an extreme looks like. Does that make sense? Okay. So that's how I like to start. And then I'm kind of mentally doing a titration where I add a little bit more base. What does that mean? When I deprotonate the first group, well, which is the first group that I'm going to deprotonate? Well, I'm going to deprotonate the group with the lowest pKa. That's how I like to approach it. If there's another way, I think that it's probably more complicated than that. But and I think I've got some videos on my YouTube channel where I do some amino acid and peptide PI calculations that I'll add to our Canvas site and I'll send those out just to see some examples. Um, but I'll tell you, diprotic amino acids, all that you do is take the two pKs, divide them by two. Done. That's all there is to it. Okay. Well, I hope that you guys have a great weekend. If something comes up, please feel free to email me and I'll get back to you as soon as I can. Um, in just a minute, I'll go and look for on my YouTube channel some old videos that I can share with you guys. Um, if I don't find any within the next like 30 minutes, then there's not any from me, but there's plenty of others on YouTube that show that same sort of thing. And I don't think that the approach is going to be radically different from mine. Um, if something comes up, let me know. Other than that, I hope you have a great weekend. Your quiz on Monday will open at 12 p.m. and will close at 11:59 p.m. So you'll have all afternoon to do it. So you don't have to like do it during class or anything like that. It's on Canvas. You'll have one attempt at it. Um, make sure that you're doing it where you have a stable internet connection. Um, but then yeah, that's all that I got. If you got some questions, you're welcome to hang around. Other than that, enjoy your weekend, everyone. I'm gonna stop my recording.